Okay, good morning. So we are back to do our consultations for the WA2. Yesterday we stopped at giant molecular lattices. Okay, so if you recall, yesterday we stopped at diamond and graphite. Okay, so I'm going to scroll right down to where we stopped. So yesterday we have gone through giant ionic, simple molecular structure, and finally we ended at the giant molecular lattice where we spoke about the two allotropes of carbon, diamond, and graphite. Now, are these the only substances with a giant molecular lattice? The answer is no. Diamond and graphite are not the only substances with a giant molecular lattice. All right. If you recall, yesterday I did say there are other substances with a giant molecular lattice. How can you tell? One way to tell is based on their melting points. If their melting points are high and it's between two non-metals, so for example, silicon dioxide. Silicon dioxide is SiO2. Si is a non-metal, oxygen is a non-metal. SiO2 has a giant molecular lattice. You could tell that based on its melting point data, because silicon dioxide has a melting point of something like 1500 degrees Celsius. It's a very high melting point. It's a very high melting point and it's between two nonmetals. Therefore, it is likely to be giant molecular lattice, and it is. All right. Now, silicon dioxide actually is quite similar to diamond. I feel the only difference is the fact that it has oxygen in it. Okay. Now, this, of course, will change how many atoms each atom is bonded to. So I think it's very important. Each silicon atom is bonded to 4 other oxygen atoms. Okay? Whereas each oxygen atom, okay, I left out a word covalently bonded. Okay, each oxygen atom is covalently bonded to 2 other silicon atoms. Okay, now how do you actually memorize these numbers? The answer is I don't. All right, I worked this out. And how did I work out 4 for silicon? Silicon is in group 14. If it's in group 14, it has 4 valence electrons. To achieve a fully filled outermost shell, silicon needs to have 4 more electrons. To have 4 more electrons means I share 4 electrons. Hence, I need to share with 4 other atoms. I need to form 4 bonds, if you like. Okay, so silicon forms 4 bonds. How about oxygen? Oxygen is in group 16, 6 valence electrons. Therefore, each oxygen atom needs 2 more electrons to achieve a fully filled outermost shell. Therefore, each oxygen atom forms 2 bonds, hence 2 other atoms. Okay, so you don't memorize, you go based on the group that the element is from, how many valence electrons it has, how many more valence electrons would it need to achieve a fully filled outermost shell. From there, you can work out how many bonds each atom will form. All right. And hence, this is actually the structure of SiO2. Now, if you just take a look at it, based on this description, definitely silicon has shared 4 valence electrons, meaning there are no valence electrons on silicon which is available for delocalization and to move freely. All right. So from this, we can actually conclude there are no delocalized electrons that move freely. So SiO2, just like diamond, doesn't have any delocalized electrons which can move freely. Therefore, there is no electrical conductivity in all states. So SiO2 does not conduct electricity regardless of solid, liquid, or gaseous state. All right? Because it does not have any delocalized electrons which can move freely. And this is because each silicon atom has already bonded to 4 other atoms. There are no valence electrons which are not shared. There are no valence electrons which can be delocalized. The next thing is the bonding type is strong covalent bonds. All right? Strong covalent bonds between what? So it's very important whenever you are explaining bonding, you must explain the bonds, the forces of attraction between what? In this case, Si and O atoms. It is the atoms which are bonding together by sharing their valence electrons. So strong covalent bonds between silicon and oxygen atoms require a lot of energy to overcome. So what can this be used to explain? This can be used to explain that silicon dioxide has a very, very high melting and boiling point, of course. All right. Now, silicon dioxide's melting point is already more than 1500 degrees Celsius. So the boiling point will be even higher than that. Okay. Now, silicon dioxide itself is a compound which has a giant molecular lattice structure. So you can see you have basically learned diamond, graphite, silicon dioxide. Now, are these the only substances with a giant molecular lattice? Again, the answer is no. There are other substances out there. So you can be asked to deduce which substance has a giant molecular lattice. How can you deduce? Like I said, melting point data might be given to you in the question. Read the question. If the melting point is high and number two, it is between two non-metals like Si and O, then you know it must be giant molecular lattice. Okay? What if the melting point was high, but it's between metal and non-metal? If it's between metal and non-metal, it's giant ionic lattice. So you need to have this mind in your head. Based on melting point, how can you tell which is which? Okay, we will do a summary of this at the end after we have gone through metallic as well. Okay, next. Now, these three are the common structures: diamond, graphite, SiO2. Okay, in your notes, we have also covered some other substances which have similar giant molecular lattices. For instance, diamond. Besides diamond, what else is also similar to diamond in terms of their giant molecular lattice? The element silicon itself. The element silicon itself is similar to diamond. It has a diamond-like structure, meaning the bonding within silicon's elements is like diamond, where each silicon atom is covalently bonded to four other silicon atoms. All the valence electrons are used for bonding. There's no delocalized electrons. Hence, silicon does not conduct electricity unless you attempted to provide more energy, but not at room temperature. Okay? Can so besides silicon, what else is similar to diamond? It's all inside the notes for covalent bonding. There are others, for instance, cubic boron nitride. Okay, cubic boron nitride is similar to diamond. Silicon carbide is similar to diamond. All right. How about graphite? What is similar to graphite? There's many. So under graphite, there's graphene. There's single wall carbon nanotubes. All right. These are two examples. There is hexagonal boron nitride. Again, is from the covalent bonding chapter 4 part 2 notes. You will need to know that, hey, there are other substances which have a graphite-like giant molecular lattice. Some substances have a diamond-like giant molecular lattice. How about silicon dioxide? Silicon dioxide also has other substances which are similar to silicon dioxide, all right, in terms of bonding. Can? So it's always based on the data that we give you. If I were to test you on, say, nanotubes, carbon nanotubes, which I did test my students in 2022, if you look at the past year paper I've given you, that was the question I said. If I were to test you on it, I'm not testing you on whether you have memorized nanotubes. I'm testing you on whether you can read the diagram carefully and realize that it's quite similar to graphite. Okay, so I would advise you to look through your notes thoroughly to ensure that you recognize from the diagram, hey, this is similar to diamond. Hey, this is similar to graphite. If they are similar to diamond, they will have diamond's properties. If they are similar to graphite, they would have graphite's properties. Okay? So that really concludes giant molecular lattice structure. Okay, so now let's move on to the last one, which is giant metallic lattice. Okay, now giant metallic lattice is also a lattice. That means it's a regular repeated three-dimensional arrangement of particles. What particles are we talking about? So you must be very clear and disciplined with your words. There are two types of particles in a metallic lattice. The first one is the positive metal ions. So like Na plus, Ca2 plus, basically ions. The second particle in a giant metallic lattice is basically your sea of delocalized electrons. Okay, so this is crucial. You need to know that a giant metallic lattice is made up of positive metal ions in a sea of delocalized electrons. All right. Now, once you realize that, the rest is quite straightforward. First, base conduct electricity in all states. It doesn't matter whether solid, liquid, or gas. Metals are going to conduct electricity in all states. And this is because they already have a sea of delocalized electrons within the giant metallic lattice that can move freely to conduct electricity. All right. So delocalized just means it's not fixed onto one particular atom or ion. Delocalized means it's not fixed, but you still need to add on that it can move freely. So the idea of movement is still important to highlight whenever you are asked about electrical conductivity. All right. So metals will conduct electricity in all states. The next thing is you will realize that metals usually, mostly, have high melting and boiling points. Not all, but most. Okay. Now, you need to know that metals have high melting points generally, and that's because there are strong electrostatic forces of attraction between the positive metal ions and the sea of delocalized electrons. And this is why the between what is very important to highlight in your answers. This is because you need to be clear. There's also strong electrostatic forces of attraction in ionic compounds. But in an ionic compound, the strong electrostatic forces of attraction are between the ions themselves. But here it's not. Here, the strong electrostatic forces of attraction in a metallic lattice are between the positive metal ion and sea of delocalized electrons. So it's between ions and delocalized electrons, which are different from a giant ionic lattice. Okay, so of course, because these are strong electrostatic forces of attraction, they require a lot of energy to overcome. Now, if you already knew this, that's good. Okay, so I hope you realize this. Now, and that's really all you need to know about giant metallic lattice structure in terms of bonding. Of course, there's other parts of this chapter, such as alloys, which we have gone through as we went through the Term 2 Week 5 database question. Why are alloys used to make coins, ornaments? Why are alloys used? Because they are stronger and harder. How do you explain that alloys are stronger and harder? Please revise this from the metallic bonding notes as well. Today, I really want to just focus on the metallic structure itself. Now, so we have learned a total of 4 structures. We have learned giant ionic lattice. That's number 1. Number 2, simple molecular structure. Number 3, giant molecular lattice. And lastly, Okay, I'm running out of space here. The last one is giant metallic lattice. Okay, I can't zoom out. I'm sorry. So I got to scroll to the right and right. Now, I would just like for us to write down these 4 structures, please, side by side. Now we're going to summarize. If I was given a question, how do I deduce which is which? Okay, and this is, I feel, your confusion. That's why we are here to solve the confusion once and for all. All right. Actually, as you read the notes, you should already have deduced all this and prepared this summary yourself. So this is an important summary to prepare for yourself. Just basically dump whatever you know about each structure down side by side to each other. Okay. So ready? First, you can tell which is which based on the elements involved. If it's a metal plus non-metal, it's ionic, giant ionic. So like sodium chloride, magnesium oxide, potassium fluoride. You know that one is a metal, the other one is a non-metal, giant ionic. Next, simple molecular usually is non-metal plus non-metal, 90% of the time. Carbon dioxide, okay? Carbon tetrachloride, CCl4. Water, H2O. H is a non-metal, O is a non-metal. Now, giant molecular, it pays to learn by heart because giant molecular is a smaller group, not so many things. That's why I gave you examples in the notes. The 3 most important examples: diamond, graphite, SiO2. But this is where you extend your understanding. Oh, diamond, also silicon has a similar structure. Silicon carbide, similar structure. Cubic boron nitride, similar structure to diamond. Graphite, also single wall carbon nanotubes. Graphene, hexagonal boron nitride. All right. So for giant molecular lattice, it pays to know. It pays to know. Finally, giant metallic is what? It's the element itself. That means sodium, magnesium, element itself. Tin, element itself. Or the alloy. What's alloy? Alloy is a mixture of a metal with another element. Doesn't matter what the element is. All right. So, like for example, that day we did in class, brass. Brass is an alloy of copper and zinc. So brass has metallic lattice as well. All right. So you need to know firstly what is inside. How can you tell from the name? The element's name tells you which is which already. Okay. Next. What are the particles inside? So firstly, giant ionic lattice, what on earth is inside it, given that it's a metal and non-metal? So first you know, okay, the forces of attraction in a giant ionic lattice are going to be called strong electrostatic forces of attraction. But don't stop there. Remember, like I said, you must know between what? So it's between oppositely charged ions or between ions. Okay? So use the right word for the right purpose. The moment the word is wrong, unfortunately, I've marked the whole thing wrong. So what are ions? Ions are like Mg2+. Mg2+ is formed when Mg loses 2 valence electron. So the idea is ions must have charge and they are formed by loss and gain of valence electron. Next one, simple molecular structure. There are weak intermolecular forces of attraction between molecules. Does it mean that there's no covalent bonds? No, there is covalent bonding in simple molecular, but the covalent bonding is inside the molecule. But I'm interested to know, to melt, or boil something that is simple molecular, what do I overcome? I overcome the weak intermolecular forces of attraction, sorry, between molecules. All right, that's simple molecular. Okay, so you can see, giant ionic, we talk about ions. Simple molecular, we talk about molecules. Different. All right, molecules are formed when the two elements, the two non-metallic elements, share valence electrons with one another. Next, giant molecular. Giant molecular is still covalent bonding. It's still sharing of electrons, but it's one giant molecule. There's no molecules. Therefore, there won't have the same structure as simple molecular. Giant molecular, you are looking at strong covalent bonds between atoms. So when melting diamond, graphite, SiO2, when melting giant molecular lattices, you are overcoming the strong covalent bonds between the atoms, be it carbon atoms or silicon and oxygen atoms. All right. Finally, giant metallic, strong electrostatic forces of attraction as well. Between positive metal ions and the sea of delocalized electrons. Okay, so this one also different from ionic, different, okay. Now, so once you have basically taken down and summarized these things, you now need to now deduce. Okay, so how am I going to use all this, right? So the idea is if it's strong, you have a high melting point. So metallic lattice, high melting point. Giant molecular lattice, high melting point, right? Simple molecular, low melting and boiling point. Both are low. Finally, giant ionic, high melting point. The melting point says a lot. Hence, you need to discern. Based on melting point, if it's low, it's confirmed simple molecular. All right. Can. So it's a very typical way of testing how do you deduce which is which. Now, how low is low, how high is high? Yesterday we said high generally means more than 500 degrees Celsius. So if something were to only have a melting point of 100 or 200 degrees Celsius, it will be considered simple molecular unless the question had provided you with additional information to read. So reading the question is very important. There are always exceptions, right? So there are possibly giant ionic lattices which have a melting point that is lower. But those are exceptions that we will give you the information to read. So the idea is in a pure chem exam, reading is crucial. If you do not read the question, I can almost guarantee you're going to go off the wrong track. All right? Can, and you don't want that to happen. So reading is very important. Please cater time for reading. Now we have solved the melting points, after which we need to go through electrical conductivity, right? So again, you summarize. Electrical conductivity, what did we learn? For the ionic compound, for example, conduct electricity. Solid state, no. Molten, aqueous, yes. Simple, right? Whereas for simple molecular, don't conduct at all. So they do not conduct at all in all states. For giant molecular, you got to be careful. Graphite. Graphite conducts. Diamond doesn't. Silicon dioxide doesn't. All right. But graphite does. Okay. Graphite has delocalized electrons that can move freely along each layer. to conduct electricity. All right. And finally, of course, metallic lattice, they will conduct in all states. So if you zoom out, come on, there's a difference, right? Ionic compounds are very specific. Ionic compounds will only conduct in the molten states and aqueous states. Whereas metallic will conduct in every state. So there's a big difference between metallic lattice and giant ionic lattice. All right. Next, to conduct electricity for ionic compounds, the ions are the ones which are free to move. All right. So it's the ions which are free to move. How about in graphite? Graphite is the delocalized electrons which are free to move. How about in metallic? Again, is it the ion or the delocalized electron? So you're going to decide, right? In metallic bonding, the one that moves is the delocalized electrons. The ions are fixed in place. All right? They are in fixed positions. So by doing this summary, you consolidate your understanding of what words to use in every question. All right? The last thing you want is to use the wrong words and the whole answer is negated. Okay? That's how strict we will be. Your answer can be all correct, just one word, atoms, molecules, ions is wrong. The whole answer is wrong because you are considered to have shown misunderstanding and contradicted yourself. Okay? Now, and that's really it for bonding. Now, bonding is vast and yet very, very fundamental. And that's why if you have misconceptions now and it's surfaced to you now, you must fix it. All right? There is no moving on. There is no moving on. So this June holidays as well, if you knew that your way of studying chemistry was flawed, and it is, because I see many of you are rushing now to study the bonding that was completed 5 weeks ago. I anticipated this. All right? I anticipated this. So let this be a wake-up call. The WA will also be a wake-up call. These June holidays, you will need to spend every single day studying 15 minutes. I'm not talking about 3 hours. Please don't do that. You need a break as well. But do not lose touch with the topics that we have done, particularly the topics in term 2, bonding, acids and bases, and mole. All right. It's not that I'm going to give you a whole lot of homework, but I think what's important is to study consistently and not forget this bonding. You will have realized by now, the ones who will do best are the ones who read daily. If you have read daily, honestly, you would have summarized all this yourself, not me. It's more powerful if you can summarize this yourself because it means that the concept is within you. Okay. And you will not learn concepts without going through misconceptions. So making mistakes is part of the learning process. If you have not made any mistakes, it's because you have not studied. Full stop. All right. The content is not simple enough to say that you will not make mistakes. So the only difference is for some of you, you are only realizing your mistake now, term 2 week 8, instead of term 2 week 4. And that's the difference. So please avoid that from term 3 onwards. From term 3 onwards, things will become much more fast-paced. I will teach much faster. Which is to say, if you are not revising every day, you will soon be lost. And worse still, if you are trying to numb yourself by not studying and only studying just before the exam, you might think that you are doing fine because you're not making any mistakes, you have no misconception, but actually you are not fine because everything is going to erupt right at the end. All right? So it's very, very important to make mistakes as you study daily, but at the same time, clarify those mistakes. If you are unsure about a word, ask what the word means. For instance, when I taught you ionic bonding in term 1, if you didn't know what an ion and an atom was, you should have asked. All right? Now, this is not blaming you. I'm just trying to demonstrate how differently you must study. Possibly in lower sec, you never asked your teachers much. Okay? But you realize in lower sec, we hardly use technical terms. Even if we did, it's very rare. But once you have reached a higher level in upper sec, you realize suddenly the whole marking scheme is based on the correct technical term usage. The moment you use the ions, the atoms, and the molecules wrongly, the whole thing is wrong. As a result, as you are learning and reading, so long as you don't understand one word, you ask that one word's meaning. Don't wait until the end. Neither should you say that, oh, I have done a lot of practice questions, therefore I will do well. It doesn't work that way. Doing practice questions without understanding the meaning of the practice question is pointless. There are some people who do the TYS and mark the TYS and they are so happy, but when the results come out, they will say, oh, chemistry is so hard. After doing the TYS, I still don't do well. And the answer is very simple. I always ask students this question. After doing the TYS, can you tell me what you have learned from the TYS? What is the point of asking this question? If you cannot answer what is the point of asking this question or setting this question, you have not learned. So similarly, this WA2, every question, every single mark has a point behind it. If you cannot tell me the point behind setting the question, that means you have not learned. All right. So even if you got A1 this time round, I will make sure you're right. Your holiday homework will be to write down for every single question, what am I trying to test? If you cannot tell me what I'm trying to test, then you have not learned from the WA, even if you got A1, A2. Okay? So this is how we should learn chemistry. Take all your homework and ask yourself what is the point behind every question. All right? Now, I'm going to move on to acids and bases very quickly now. Now, I'm not going to go through everything, of course. I can't, right? But I think what you need to go through really is the main reactions. Okay, so I would say there are 4 main reactions first. We will go through the reactions first, then we will revisit the definitions of weak acid, strong acid. But let's start with the reactions first. So acid plus metal, salt plus hydrogen gas. This one we should remember, right? Acid plus base, salt plus water. Okay, that's the second reaction. The third reaction, acid plus carbonate, salt plus CO2 plus H2O. Okay? And lastly, what is the fourth reaction? The fourth reaction involves a base. A base with an ammonium compound. Now, you might see sometimes we write ammonium compound, sometimes we write ammonium salt. Basically, anything with ammonium ions in it will be fine. Okay, and this reaction, base plus ammonium compound, forms salt plus ammonia gas plus water. Okay, so that's the first step in revision, memorizing these general reactions. The next step is always to circle up the gases. Once you have circled the 3 gases amongst the 4 reactions, it's immediately clear. There's one reaction where there's no gas, and that is acid plus base, right? Acid plus base forms salt and water. There's no gas formed. Meaning, acid plus base will not have bubbles. Acid plus base will not have effervescence observed. Next, you need to know the tests for these 3 gases and the observations. When we ask you to describe the test, we don't just mean describe the test. You must state the test and the observations. Hydrogen is a good example. Describe the test for the gas hydrogen. Insert or place a lighted or burning splint. The gas extinguishes the burning splint with a pop sound, right? Or lighted splint with a pop sound. Lighted and burning means the same thing. Okay, so this is what you learned in Sec 2. Tests for hydrogen. Now we move to the tests for CO2, carbon dioxide. What do? Not just use lime water. You can't use lime water. You have to bubble the gas into lime water. Use lime water is not acceptable because how are you going to use it? You got to be specific, right? So you got to bubble the gas into the lime water. The gas forms a white precipitate in lime water. That's for CO2 gas. Okay. Next one, ammonia. Ammonia gas is NH3. So you got to remember, ammonia gas is an alkali when dissolved in water, right? So ammonia gas being alkaline when it dissolves in water, the best thing to do is to place a piece of moist red litmus paper at the mouth of the test tube, assuming that you use a test tube. Okay, most of the time we use either a test tube or boiling tube, depending on the question. So we place a piece of moist red litmus paper at the mouth of the test tube, boiling tube. The gas turns moist red litmus paper blue. Okay, so the second step is to study the gas test. So the first step, study the reactions, like memorize acid plus metal forms salt plus H2, acid plus base forms salt plus water. Okay, the second step is to study the gas tests. The third step is now to try writing examples of chemical equations for each reaction type. Of course, we're not going to go through every single thing. All right. In your daily life, you could write example equations, right? Acid plus metal, for instance. Acid plus metal. Just choose any metal that comes to your mind. So let's choose acid, HCl, metal, magnesium. It forms a salt, and the salt is called magnesium chloride, MgCl2 plus H2. To balance, I need 2 in front of HCl. Now, you can see I'm doing it so fast. Of course, because with practice, we can do this fast. So where on earth do you get such practice? From the notes. The notes alone, if you add up, you have something like 40 equations. Besides that, I've also given additional practice. That's another 30 equations. That's 70 equations in total. You could practice writing 70, right? That will make you much, much faster in balancing. All right. In fact, after working on some time, I'm sure you realize there are a lot of useful patterns. For instance, you will have realized if it was not magnesium but zinc, the equation is literally balanced the same way. All right. Even without writing now, I can tell you zinc is going to be balanced the same way as magnesium metal, simply because zinc forms Zn2 plus. So the formula of the salt is similar, ZnCl2. That's why 2HCl is needed. So as you practice the 70 equations, you should see a lot of patterns, and that helps. All right. Now, of course, these are the chemical equations without state symbols. So do you write state symbols or do you not write state symbols? It depends on the question. If the question required you to write state symbols, they will say so. So if the question says write a balanced equation with state symbols, then you include state symbols because marks are given for that. But if the question did not state to write state symbols, don't write because it will take up your time. Not that if you write, we are going to mark you wrong. It's that you are penalizing yourself in terms of time. Do not do unnecessary things because you are wasting your own time in a very, very tight exam setting. All right. So in this case, if I didn't say, don't write. But what if I did say? If I did say, how do you write? For instance, okay, let's say zinc reacted with sulfuric acid. So you will need to write the state symbols. Let's say, if I say write the state symbols, the state symbols come in this form. All right, just a very quick recap. Aqueous means dissolved in water. So what is aqueous? Well, the acids must be aqueous. If they are not aqueous, the acids do not produce H plus ions. They do not dissociate and ionize. Must be aqueous. The metal is a solid. Metals are solids, right? They are solid iron, solid zinc, solid magnesium. However, the salts are solutions. They are soluble. Soluble means aqueous as well. All right. Most ionic compounds, which are salts, are soluble. Finally, hydrogen is a gas, right? It's a gas. Now, and this is also where we can practice. This is called the chemical equation. How will you write the ionic equation for this reaction, the same reaction, right? So, if you look at the chemical equation, you must first have a chemical equation that's balanced. It's balanced, all right? The next step, the chemical equation must have state symbols. If you don't have the state symbols, you cannot go on to writing ionic equations. All right. So now let's practice. How do we write ionic equations? We need to split up the substances into ions formed. But we only split up those which are aqueous, meaning anything that is not AQ, we should not split into ions. Clear? So in this particular reaction, we will only split up H2SO4 and ZnSO4 into its ions. Next, there are rules to this. You need to know H2SO4 is called sulfuric acid. Acids produce H plus ions. It's a must, it's a definition. Acids are substances that dissociate and ionize to produce H plus ions when dissolved in water. So H2SO4 must form H plus. The question is how many, right? Quite clearly, there are two hydrogens which can be dissociated. Therefore, 2H plus, twice the amount of H plus is produced. This is why sulfuric acid is called a dibasic acid, because it produces 2H plus per H2SO4 dissociated. Okay, so H2SO4 can be split up into 2H plus because it's dibasic. Next, sulfate, SO4 2 minus, right? So whatever that remains is SO4 2 minus. It's also aqueous. We do not split up zinc because zinc is a solid. Anything that's solid remains as is. Copy and paste. The next one we come to is ZnSO4, which is aqueous. If it's aqueous, must split into its ions. So what are the ions in ZnSO4? The name tells you it. The name is zinc sulfate. So it's Zn, zinc ion is Zn2 plus, aqueous. Sulfate is SO4 2 minus, aqueous. So that's how it split up zinc sulfate into its ions. Finally, hydrogen is a gas. We do not split it up. So it's H2 gas, just copy and paste. Now, the purpose of splitting up into ions, of course, is to show you which ions have not changed, meaning which ions are the same throughout. Over here, it's quite clear. The sulfate ion, SO4 2 minus, has remained the same throughout. So sulfate is a spectator ion. It just watches the reaction, it didn't change. So we can cancel it out boldly on both sides of the arrow for the ionic equation. So the ionic equation basically is a summarized version of the equation, which expresses to you which ions have changed, which ions have not changed. Why are we so interested in change? Because a chemical reaction is a change. We want to know what has changed. We are not interested in what didn't change. So, since sulfate ion didn't change, we cancel it out, which means we are literally left with everything else. And this ionic equation is useful because it allows us to see what exactly has happened. What happened is zinc metal, the zinc solid metal, has somehow kicked out H plus, right? It kicked out the hydrogen ion to form hydrogen gas. Another way to say kick out is to displace. So zinc has displaced hydrogen ions from the acid. All right. Now, the next important piece of information that we can get from this ionic equation is, hey, so basically zinc has now formed its ion, whereas hydrogen has gone back to its elemental form without a charge. That's another useful piece of information. Now, finally, if I were to compare the chemical equation, which is on top, and the ionic equation, which is below. Chemical equation should not have any charges. The chemical equation doesn't have any charge because the charges are supposed to be balanced, right? ZnSO4, Zn2 plus, SO4 2 minus. So the charges cancel out. It's neutral electrically. So a chemical equation must never, ever have plus or minus charge. That's a chemical equation. An ionic equation has charges. Ionic. So it has ions to be shown. Why does it have charges? Because we cancelled out the spectator ion. So because we cancel out the sulfate, it's no longer there in the ionic equation's answer. Therefore, whatever is left was its partner, Zn2 plus or H plus. Okay? Can? Now, so just a recap, this is a quick recap how to write ionic equations. Of course, there are other ionic equations that you could write. You could write ionic equations for every single chemical equation as a good practice. All right. So another good way to practice ionic equations, of course, is to go back to the notes and practice writing them. Another way is to make use of the equations that you have already written. Now try writing their ionic equations to let me take a look. Okay. Now, just a recap, we only dissociate those aqueous ones into ions. So acids must dissociate into H plus and the other ion. The salt must dissociate because it's aqueous. Okay? So anything that is aqueous, we split into ions. All right? Now, we are still on acid plus metal. Okay? We are still on acid plus metal. So you can see we have gone past just memorizing. We are now at the equation writing stage. Now, the ionic equation is particularly interesting because the ionic equation shows you that the metal is displacing the hydrogen ion. Now, how does this work? This works because metals have different reactivities. The reactivity series of metals, which is in the notes, must be learned. So this is the reactivity series of metals that I'm writing out. You notice that the reactivity series of metals includes hydrogen, even though hydrogen is a non-metal. And the reason is because the way to predict which metals react with acids is to look at its position. Those metals like potassium, sodium, calcium, magnesium, aluminum, and so on, those metals which are above hydrogen in the reactivity series, they can displace H plus from acids, meaning they can react with acids. So anything above hydrogen in the reactivity series will be able to react with acids. Whereas copper, silver, gold, all your precious metals, platinum, another precious metal. Metals like copper, silver, gold, platinum, they are below hydrogen in the reactivity series. They cannot displace H plus from acid. All right. If they cannot displace H plus from acid, they do not react with acids as a metal. So the metals like these don't react with acid. So copper metal doesn't react with acid. Copper 2 carbonate can react with acid because that's the carbonate. But here I'm talking about the metal. So copper metal does not react with acid. Okay? Which is why your coins are made of copper. Your jewelry is made of silver and gold because coins and jewelry are meant to last. Imagine if they were to react, if you poured vinegar on them, vinegar is acidic. Imagine if they reacted. right? Your coins will disappear, your jewelry will disappear. That's why copper, silver, gold, they are not reactive with acid. They do not become corroded by acids. All right? Okay? And that's what you learn from part A. Now, you notice it's under reactivity series. Oh, it's not one of the chapters tested, right? Oh, no, that's not true. So long as it's in my notes, it's tested. All right? I expect my students to know this, including the reactivity series. And that's why I taught it in class over one lesson, a double period, right? So that you are familiar with this. Okay? Now, we can continue writing equations for acid plus base, acid plus carbonate. Okay, so I'm just going to do a quick example. Okay, I'm going to use zinc as an example throughout today. Okay, so HCl plus, let's say, ZNO becomes ZnCl2 plus H2O. All right, again, we balance it quite easily by adding 2 in front of HCl. That's acid plus base. Then we have acid plus carbonate. I'll also use zinc carbonate as an example. Again, put 2 in front of HCl and everything's balanced. All right. So that's the idea. Acid plus base, acid plus carbonate. So practice writing the equations. Of course, it's the whole test about equations. Are you going to be given like 5 equations to balance? No. And for pure chem, you will notice the equation writing is always from context. So you will need to read a whole paragraph, figure out what's reacting with what to write the equation. Okay, there will not be a question where write an equation for this plus that. It won't be so simple. You will need to read the whole paragraph. That's why it's called database, right? Okay. So that's acid plus carbonate. And finally, let's finish the ammonium compound one. So let's use calcium hydroxide plus, let's say, ammonium sulfate. It forms calcium sulfate plus ammonia gas plus water. But again, you need to be careful. Okay. I have 2 ammoniums, therefore I have 2 ammonia. I have 2 OH, I have 2 H2O. The number of ammonia is linked to the number of ammonium. The number of OH is linked to the number of water. All right. Now, at this stage, any questions about equation writing and acid plus metal, acid plus base, acid plus carbonate, and so on? So a good practice is to balance the equations yourself again. Even better practice is after balancing the chemical equations correctly, try writing the ionic equations as practice. Okay? It's important to practice. Of course, with more practice, you become more automatic. And by now, you should recognize some common formula. For instance, for like calcium hydroxide, there should not be a need for you to think so hard. Calcium is group what? Calcium is what charge? What is hydroxide? If you need to think so much, that means you're not familiar enough. Calcium hydroxide is Ca2 plus OH minus Ca bracket OH2. By the end of the practice of 70 equations, you should remember a lot of common formula. Okay. Now you need to remember this formula fast also because when you move on and do more advanced chemistry, you will be asked to balance the equation yourself, right? But after the equation balancing, there's many other things to do. You may need to do mole concept and so on. So if you are spending a long time balancing, it's going to impact your speed in finishing mole concept later on, which is WA3, right? So it's very important to ensure that your balancing is also fast but accurate. And this is the time to practice, which is why WA2 is used, is the point where it's again a reality check. How quick are you in terms of balancing equations and formula writing? And like I said, I mean, I'm glad that the 8 of you here, you are practicing very hard. I sincerely hope the rest of the class is as well. All right? Because these are fundamental skills that cannot be ignored, which is why this whole term we focus on all the fundamentals, bonding and equation writing. We didn't do practical for a good reason, because the practical skills is the next term when we actually do the practicals to support what we learned. But you must have the fundamental skills first. So if the fundamental skills are no good, again, these June holidays must work on balancing equations. All right. Now, I'll just quickly move on if there are no questions. We mentioned in class, calcium hydroxide is a base. We should know this because it's a metal hydroxide. So it's a base. Now, this is not just any base. Calcium hydroxide is a specific base that is added to neutralize acids, excess acids in the soil. Now, whenever you want to support plant growth, you need to ensure the soils that the plants grow in are not too acidic. So to neutralize the excess acids, let's say if it's too acidic, there's too much acid, you will need to ensure that you add a base. But you don't just throw random bases down. There are so many bases to choose from. For instance, you could have chose sodium hydroxide. It's also a base, but you won't do that because sodium hydroxide, number one, sodium hydroxide is too alkaline. It's not just going to neutralize, it's going to make the soil alkaline. The plants will die as well. Number two, sodium hydroxide has sodium ions, Na plus. Sodium ions are toxic to plants. So you don't just throw random things in. You need to ensure that whatever you throw in will not kill the plant. So calcium hydroxide is the best option because calcium ions are not toxic to the plants. Number two, calcium hydroxide is still a base that can neutralize the excess acids in the soil. All right. Now, ammonium sulfate, or rather any ammonium compound, you could have used ammonium chloride, ammonium nitrate as well. Ammonium compounds are fertilizers. You need fertilizers. In particular, you need the nitrogen in fertilizers for the plants to grow well. So this reaction shows you that it's going to be problematic if you added fertilizer and the base at the same time to the soil. If I added the ammonium fertilizers and calcium hydroxide at the same time to the soil, you produce ammonia gas, which escapes. The gas will escape from the soil, obviously, and this causes a loss of nitrogen from the soil, which depletes the nutrients available in the soil for the plants to grow. So please don't add ammonium fertilizers at the same time as calcium hydroxide. Okay? Next, the final part of the chapter is on types of oxides, which you should not ignore. Now, similar to your notes, we are going to draw a flow chart, but it's not difficult. Metal oxide, non-metal oxide. So the first question you got to ask yourself is it a metal or non-metal that's with the oxide? Now, under metal oxides, there are two types. The first type of oxide is basic oxide. The second type of oxide is amphoteric oxides. Okay, so most metals will be here, basic oxide. So magnesium oxide, calcium oxide, these are basic oxides. Basic oxide means what? It's a base. Basic oxide means it's a base. That means they react with acid. Base plus acid, right? However, they do not react with base. Okay, they do not react with base. So acid, okay, they react. Base, they don't react. All right. Now, amphoteric is a specific group that you must remember, the ZAP, zinc oxide, aluminium oxide, lead 2 oxide. So ZAP, zinc, aluminium, lead. Are these the only ones though? The answer is no, there are others as well, just that these are the most common three that you must memorize. So what about the others? You can't memorize everything on earth, but we can do experiments to find out, right? A good way to do experiment to find out is if it's amphoteric means it react with acid, yay. But it also react with bases. It reacts with both. Okay? So an amphoteric oxide will be able to react and dissolve in HCl. It will also dissolve in NaOH. That's the meaning of amphoteric. All right. So the way to do experiment is, if I wanted to distinguish basic from amphoteric, if I want to differentiate whether something is basic or amphoteric, I will add base. I won't add acid, because if I know that they are either basic or amphoteric, both will react with acid. I can't tell the difference. I will only tell the difference between basic and amphoteric by adding base, like NaOH. Okay? The idea is to differentiate, right? So to differentiate, we add a base. Now the non-metal oxides. Non-metal oxides, most non-metal oxides are acidic. That means they dissolve in water to form acids, acidic solution. All right? So most non-metals are here. So like SO2, sulfur is a non-metal, so SO2 is acidic oxide. NO2, acidic oxide. Nitrogen is a non-metal. CO2, acidic oxide. Even an unlikely non-metal, SiO2, silicon is also non-metal, so it's acidic as well. Now, there are more, of course, there are more, right? I mean, I could name some more. P4O10, wow, complicated, but it's an oxide with phosphorus, right? Phosphorus is a non-metal, so also acidic. Okay, so all these are acidic oxides. Acidic oxides means they react with base, but they do not react with acid. Okay, so acid plus base, there's a reaction, but acid plus acid, no reaction. So if you are already acidic, you can't react with acids further. Okay, and most non-metals will be there. That means don't go and memorize. Don't need to memorize. You just need to know non-metals form acidic oxides. That's it. Of course, the ones that you need to memorize are the last category for non-metals, the neutral oxides. And this one is very easy to memorize. The conoho, CONOH2O. These are all neutral. If they are neutral, means they do not react with acid and bases at all. There's no reaction. All right. That's why it's called neutral. All right. So these are the 4 types of oxides: basic, amphoteric, acidic, and neutral. Again, these are all in the notes. All right. They are all in the notes, including this flowchart. So as you study, a good strategy in studying is, as you read, don't just read passively. Take out a pen and doodle. Doodle by drawing your flowchart out yourself, and ensure that you tick, cross, cross, so that you know what it reacts with, what it doesn't react with. As you do this over a long period of time, you will have developed so much competence in you and familiarity in you that this is straightforward and simple. Okay? Now, this really brings us to the end of the consult. All right. So I'm going to stop the recording here. Thank you.